So this is the last talk before the lunch. Let me introduce Piotr Nowak, is specialist in geometric and analytic group theory, index theory, non-commutative geometry, and topology of manifolds. He got PhD in 2008 in Vanderbilt University, and then he worked in Texas A&M and Mathematical Sciences Research Institute in Berkeley. So, well, he has many awards, among them, but mentioned just recently got the main prize, Stefan Banach Prize. This is the prize, the main prize of the Polish Mathematical Society. He's a holder of ERC grant, starting grant, rigidity of groups and higher index theory, in short, index. Okay, so thank you very much, and the floor is yours.
Thanks a lot. All right, so I'll be writing on this electronic board. Okay, so what I'd like to talk about are spectral gaps and applications to index theory, in particular, their relation to various versions of the Baum-Connes conjecture. So what I want to start with is a fairly simple notion, and this will be a notion that we will start with, expanders. So what are expanders? So a sequence of expanders is a sequence of finite graphs gamma I with vertices and edges, such that two things happen. So first of all, they all have bounded degrees. Uniformly bounded degrees. And the second one is that sets have uniformly large boundaries. So this is denoted by what is called defined by what is called the Cheeger constant. So here I take the infimum over subsets of the vertices, so I consider the boundary, and the boundary for a subset of vertices is it's a set of edges that connects the given set to the complement, right? So edges in E has exactly one vertex in A. Okay, so the idea is that this infimum is bounded below by a constant C for every gamma I, right? So this should be VI, and C is independent of I. So it's for every vertex, you look at the number of edges that go out of the vertex, and the degree is, this just means that this happens at every vertex. The bound is uniform everywhere. Okay, so what does this mean? So geometrically, this means that we have a sequence of finite graphs. Oh, I should add that the cardinality of the i's goes to infinity, right? So we want these to be larger and larger. So the idea is that we have a sequence of graphs in which every set of vertices has a large boundary, right? So we don't have sets of small boundaries. So if you, for example, if you would take a cycle, then you can take, or a sequence of cycles, right? So then you would have very long, if you take half of the cycle, you have a very large set, and the vertex set, the boundary is always two edges, right? So for instance, a sequence of cycles is not a sequence of expanders. Okay, so expanders satisfy intuitively two counterintuitive properties. So they're both sparse and well connected. So they don't have many edges. That's controlled by the bound on the degree. But at the same time, they have a lot of connections because every set of vertices has a lot of connections to the complement. Okay, so they're hard to separate. For instance, you have to take out a lot of edges to separate the graph into two pieces. Okay, and there's another description. Of this notion. Okay, so I can fix an orientation, any orientation on the edges, and I can define an operator from L2 of V into L2 of E, and the F of E is F of E plus minus F of E minus. Okay, so this is the discrete gradient. So depending on what your preferred point of view is, this could be the discrete gradient, this could be the codifferential. It's all of those things. And we can define the Laplacian which is D star D. This is an operator on L2 of V. Okay, so gamma I is a sequence of expanders if the Laplacian, so maybe I should write gamma. The Laplacians of gamma I have a uniform spectral gap. What that means is that the spectrum of gamma I is contained in zero disjoint sum with some interval where C, this C is independent of I.
Are you assuming your graph is correct?
Yeah, sure. Yeah, sorry. Yeah, that's always an assumption. Yeah. Thanks. Okay, so this is an analytic description of what it means to be an expander, and it just means that these Laplacians have a uniform spectral gap for all of these graphs. Okay, so expanders are very useful. And this is a very active topic of investigation currently. So the obvious first observation is that these are perfect models for robust networks. So whenever you want to build a network which is well connected, but you're limited on resources, so you want to limit the number of connections or edges, or whether it's an electrical network, I don't know, computer network, whatever it is, these serve as very good models because they're very hard to separate and they have few edges, but still maintain high connectivity. They are very good examples of spaces with exotic geometric properties in metric geometry. So for instance, they don't embed nicely into any Hilbert space. So you cannot embed these graphs Definitely not isometrically, not bi-Lipschitzly, not even what is called coarsely. So it's a very weak form of an embedding. The reason is that they are so well connected that whenever you embed them into a Euclidean space, things get collapsed. Okay, and they are also useful in computer science. So for instance, they can be used to design various algorithms. One of such algorithms, the type of algorithms are streaming algorithms. So these are algorithms which, for instance, sort. If you look on Twitter, there is a list of trending phrases. So these lists of trending phrases are put together by a streaming algorithm. So the algorithm acts as a gate through which data passes. So the algorithm sees each piece of data only once, and it has to decide which pieces are the relevant ones, the ones that appear most frequently. So for instance, what you can do is you can design optimal streaming algorithms using expanders by decomposing this data into different pieces and then gluing them back together using the expander graphs. Okay, so I will mention in a second one more application, which is in index theory. But before I do that, that's the one we'll discuss in detail. But before I do that, they are hard to construct, and there are two, maybe three ways to construct expanders, and the first one goes back to Margulis in 1977, who showed the following. So if G is a residually finite group with property T. So residually finite means there exists a sequence of finite index, and I is finite index normal subgroups, and their intersection is trivial. Okay, so you have this family of less and less dense finite index subgroups in your group. So if G is a residually finite group with property T, so property T is a certain analytic property of the group introduced by Kazhdan. I won't get into that. Then Cayley graphs of the finite quotients are a sequence of expanders. Okay, so combining this theorem of Margulis with previous results of Kazhdan on property T, you get SLN Z mod PZ. These give you with elementary matrices the generators for n greater or equal than 3. These give you expander graphs. And these are the classical examples here. You can so whenever you have a residually finite group with property T, you get this as a consequence. Okay. Okay. There's also I should mention an amazing result by Damian Osaida, for which he got the Banach Prize I think last year, is that there exist finitely generated groups which contain certain expander graphs. Isometrically in the Cayley graphs. So this is a very difficult thing to do. So the first versions of these were announced by Gromov 20 years ago, but there was no proof. Just essentially just an announcement. And Gromov said that there are some groups which can contain expanders in a very weak way in their Cayley graphs. And so what Damian proved is he actually showed that there can be a group with an isometrically embedded sequence of expanders. Okay, so this is more of a side note, maybe. Okay, so expanders are useful. So what I want to mainly talk about is how they are useful in disproving certain conjectures in index theory. So index theory, the main sort of result from the 20th century is the Atiyah-Singer index theorem, which says that if you have a compact manifold, you can take an elliptic operator on that manifold, and it has a well-defined Fredholm index, which is on a certain Hilbert space, it's the difference between the dimension of the kernel and the dimension of the co-kernel. What they showed is that this number, which is defined completely analytically, can be actually expressed in terms of cohomology classes. So this was an amazing result, and it was then pushed further by many people, but one of the main attempts at generalizing this theorem to the non-compact setting is the Baum-Connes conjecture. So the Baum-Connes conjecture is phrased in terms of a certain map in cohomology, in K-theory, and by now, so it was formulated in the 80s, but by now there are a few different versions of the Baum-Connes conjecture, and what I want to focus on is one of these, which is the Baum-Connes conjecture, and this so I'll write it down and I'll say what the elements of this formula are. Okay, so this is so the Baum-Connes index map. So this goes from the coarse K homology. Y here is a discrete metric space. You can think of a finally generated group, discrete metric space. So this is what is called the coarse K homology. So there's a certain, so you take K homology of this space in a certain way where you kind of kill all the local information and just preserve the large scale information. In general, K homology can be thought of in terms similar to the original Atiyah-Singer index theorem. So K homology is in general formed by equivalence classes of elliptic operators taken in a specific way. So these can be thought of as large-scale elliptic operators, whatever this means. And this is, so the map is the index, and it assigns, in the classical theorem, it assigns a number. In all of these generalizations, this number becomes a K-theory class. Okay, so this is the K-theory, analytic K-theory. And this guy here is the row algebra, which I'll define in a second. So this is a C-star algebra that's that's constructed for a given metric space. So the conjecture is usually defined in this form of way, that it's a map from K homology to K theory of appropriate objects. And the conjecture is always that this map, nu I, is an isomorphism. Okay, so yeah, so this is more or less how this conjecture is formulated to actually introduce all these elements precisely. It's quite a bit of work. So what I want to only do is to describe the row algebra. So the row algebra it's a subalgebra. So Y is our metric space. And I can look at the space L2 of Y, so the Hilbert space of square summable functions on Y. And I can look at a certain C-star algebra of operators on this space. Okay, so the operators, they can be expressed in terms of matrices, infinite matrices indexed by Y. And here's the main diagonal, and the operators I want to consider are ones which are supported in finite bounded strips along the diagonal. Okay, these bounded strips, so this is d x y is less or equal than n. Okay, so this is the bounded strip. Okay, so these are called finite propagation operators.
If I apply this to a characteristic function at a point, then I get something which is supported on some ball around that point. But
Apply what? Sorry. If I apply.
I mean, you draw your picture as if Y was just the images, right?
Yes. Sorry. So in general, it's, for instance, in most situations, it will be okay. So it will be some discrete metric space.
So if I take a function supported at one point and apply the operator, then what I get is supported on some ball of
yes, exactly. So the abstract definition is that there is a number such that the operator does not move supports of functions further than that number from the original. Yeah, that's the bounded propagation. Bounded propagation operators are defined this way. Yeah. Because in general, if your space is not discrete, that's the kind of definition you want to work with. So this is the finite propagation condition, and the row algebra, the uniform row algebra, the uniform row algebra is simply the closure of these finite propagation operators. In the space in the algebra B of L2 of Y. Okay, so this is the row algebra. C star Y is is a variant of this construction where instead of numbers here as coefficients, I can have locally compact operators on some other Hilbert space. Okay, so these are locally compact finite propagation operators. So this is a very nice natural C-star algebra that's very useful in all sorts of metric settings. And okay, so maybe let me describe. So the Baum-Connes conjecture that I wrote is not true in general. Okay, so there is a counterexample. There is a class of counterexamples. Here is a theorem due to Hickson, Vincent Laporte, and Scandalis. I think this was 2003, maybe. Expanders do not satisfy the coarse Baum-Connes conjecture. Okay, so the idea was very simple. Okay, so I have my so what they want, yeah.
So just quickly, because you define an expander as a sequence of finite graphs.
Yeah, so you can turn it into a metric space. You just take the disjoint union of all these and right. So Y is a disjoint union of these gamma i's. Yeah, you have to define the metric between them in some nice way so that they are spaced out and not clumped together, and so that they don't mess with each other's geometry. But it's easy to do. Okay, so what they did is they showed that this map is not surjective, right? So this map, this map goes from K homology to the K theory of the C-star algebra, of the row algebra. So what they showed is that there exists a K theory class here that does not live in the image. Okay, so K theory classes in analytic K theory are given by projections in matrix algebras over the given C-star algebra. In fact, they actually constructed an example in the algebra itself. So it's an equivalent of a line bundle. Okay, so here's the projection that they constructed. So you take on each graph, right? So this is these graphs are getting larger and larger. And this is gamma 1, gamma 2, gamma 3, and on each graph you just take the averaging operator, okay, and you take their direct sum, and this direct sum is an operator. It's an operator on L2 of Y. Okay. All right, so the first question is, why does this actually live in the row algebra? So the row algebra is these are the limits of finite propagation operators, and this thing actually grows, right? So this does not seem like it should live in the row algebra. But actually the fact that these are expanders and that you have this spectral gap actually allows you to prove this, that this guy lives inside the row algebra. The reason is that this projection is simply on each of the graphs. This projection is the projection onto the constant functions on the graph, right? And so this is exactly the kernel of the Laplacian. So if you have the uniform spectral gap, that means that the spectral projection, you can take the spectral projection associated to 0 on each one of these graphs. And because the spectral gap is uniform, it actually you can actually do it in this large algebra. So if you look at the Laplacian on all of these graphs inside the row algebra, which is the finite propagation operator, then this is the spectral projection associated to it, and you can take it within the C-star algebra because there is a uniform spectral gap. Okay, so spectral gap. Means that this P belongs to C star of Y. Okay, and as such, it gives rise to a K theory class. And then there's another argument, which maybe I won't write down, but well, you then have to show that it doesn't live in the image. So what they do is they take two traces lift to K theory, and they show that there are two, actually not traces, but trace-like maps, which are equal on the image of the Baum-Connes conjecture, of the Baum-Connes, coarse Baum-Connes map, but they differ for these two projections. Okay, therefore they differ for this projection. On one, the one trace is 0, and the other trace is 1 for this. So that's how they show that that you cannot actually that this projection gives rise to a K theory class that does not live in the image of the coarse Baum-Connes map. Okay, so maybe what I wanted to mention is some work that we've been doing with that we've done here with some of the postdocs that were here with Han Li and Sanas Puya. And basically the statement is that there exist higher dimensional versions of this argument. And as such, we have a strategy of finding new different from the previous one's counterexamples to the coarse Baum-Connes conjecture. Okay, so I'll briefly mention how this is done. So basically, what we want to do, what we do is we reinterpret this projection. Okay, so this projection on each graph that just averages on each graph and projects onto the constant functions on the vertices. Right, so this is from L2 of V onto the constant functions on V. We reinterpret this as you can view this as the projection which lives actually in cohomology. So this projects onto from the cochains, zero cochains, which is this is finite dimensional, right? So if I write L2, it doesn't really do anything. Onto the zeroth homology group, with coefficients in R. Okay, and then for a group, for G residually finite, with the sequence of finite index subgroups, we can take the cohomological Laplacian. So if I have, so the setup is now group cohomology with coefficients in some unitary representation. Okay, so here I have dn minus 1, and the cohomological Laplacian I have, since I'm in the Hilbert space setting, I can define it the usual way. Okay, and this is a higher dimensional, or one of the ways to view a higher dimensional analog of these graph Laplacians, right? So if my graphs come from this Margulis construction, so they're actually quotients of a residually finite group, then the zeroth, the Laplacian in degree 0 fits into this picture. Okay. So what I want to do is I want to take the cohomological Laplacian, and this cohomological Laplacian for every group, this is a matrix of some dimension, right? So the dimension will depend, for instance, on the number of cells in your Eilenberg-MacLane space or something like this in the given dimension. And pi is my unitary representation that defines my module structure. And So they live in the image under this representation of the real group ring. Okay, and the matrices over that image. Okay, so the theorem that we proved, I'll just formulate it and maybe comment on. So if G, I need to assume certain things on the group. So exact is one of these assumptions, which is very mild, residually finite group, finitely generated of type Fn+1. This means it has an Eilenberg-MacLane space with finite n+1 dimensional skeleton. Ni is the sequence of finite index subgroups. Which intersect at the identity. Assume that lambda, there exists a lambda, so this will be the spectral gap, such that the n-dimensional Laplacian for every group Ni has a spectral gap at least lambda. So again, that's the same, right? So the spectrum of delta n and I is contained in 0 with lambda infinity. And now if the Baum-Connes conjecture holds for the quotients, right, for the disjoint union of the quotients, then we have the following statement, which is a statement about Betty numbers of the group. Okay, so this is the L2 Betty number. And this is the standard Betty number. So this is just the dimension of H and Ni C. Okay, for all but finitely many I. Okay, yeah, so this is a statement which says the following. So if we have the uniform spectral gap, now instead of having it in degree 0 for the Laplacians in degree 0, so for the graph Laplacians, we look at the cohomological Laplacian in degree n, and if they have a uniform spectral gap, then if the Baum-Connes conjecture holds, then we have to have a certain statement about the Betty numbers and the L2 Betty number of these subgroups. So what this does is this gives a strategy to find new counterexamples. So we need spectral gap for a spectral gap for these delta and I, right? We need the L2 Betty numbers are not equal to the Betty numbers for infinitely many I's. And if we have these two, we have that the Baum-Connes conjecture fails to be surjective, or the Baum-Connes map fails to be surjective. So the conjecture fails. And ideally, this is the key thing, which we don't know how to. So we can construct guys like this at the moment. But the key thing would be to have that G over Ni do not contain expanders. So this third part would make these counterexamples essentially new, right? Because otherwise, so what we can do is we can construct things where these high dimensional things do happen. However, we do not know how to get rid of. They still do contain expanders, and getting rid of the expanders would actually be something quite beneficial. It will give a truly new class of counterexamples. And so this coarse Baum-Connes conjecture is a metric version of the Baum-Connes conjecture. The main Baum-Connes conjecture, the classical one, is still open, but understanding how the metric one fails could bring us a little bit closer to trying to understand how the classical one can fail. All right, so I think this is what I wanted to say. Thank you.
Thank you very much. Questions? It was so clear that. So, thank you very much again. And as I said before, you're all invited to the lunch. Or up. You're free to go. The way back from lunch, and grab the poster from the city or institution. These are the posters for the Spanish Polish meeting of mathematicians to the in Łódź this year. So resume at 2 o'clock.
Teraz